Good afternoon. It is almost, if not exactly, 2 o'clock Central European summertime, and I suggest we get started. Welcome everybody to our webinar. My name is John Vos from BTG in the Netherlands, and I will be one of your moderators this afternoon. Working with me this afternoon is Thies Vellenberg from FNR in Germany, who will moderate the questions and answer sessions that follow each of the 3 speakers' presentations. As you may have read in the invitation, today's webinar is jointly organized by 3 initiatives, supporting and promoting the deployment of bioenergy. All 3 have received financial support from the European Commission. The main organizer is MUSIC, which is an acronym referring to Market Uptake Support for Intermediate Bioenergy Carriers. The MUSIC project helps developing feedstock mobilization strategies, improving logistics, and setting up trade centers for intermediate bioenergy carriers like torrefied biomass, pyrolysis oil, or microbial oil. Co-organizer BIOFIT facilitates the introduction of bioenergy retrofitting in 5 industry sectors. Co-organizer ETIP Bioenergy is an industry-led stakeholder platform engaged in the development of sustainable bioenergy and competitive biofuel technologies. The webinar today is a follow-up on an introductory webinar addressing the basics of fast pyrolysis of biomass that was held 2 weeks ago on Monday the 25th of May. And a video recording of this webinar is available through the ETIP Bioenergy website. Today we will zoom in on the upgrading of fast pyrolysis bio-oils, and we have secured 3 speakers that will inform us on the latest development in these fields. Our first speaker is going to be Dr. Rune Lødeng, who is a senior scientist at SINTEF from Norway. He will talk about the upgrading fast pyrolysis bio-oil by co-hydrodeoxynation and co-hydrotreating. But before we give the floor to Rune, I'd like to remind you of some practicalities. And for some reason, all participants are muted, as you will have noticed. The webinar will be recorded for later viewing. Questions can be raised at all times through the chat box, and questions will be addressed at the end of a speaker's presentation. My co-moderator Thies will moderate the Q&A session, and through the chat log we will collect all questions. Should we not be able to answer yours during the webinar itself, we will include them in a Q&A document that we can provide afterwards. The webinar will be recorded, as will be the chat log for later viewing, and it will be made available, among others, from the MUSIC project website. I guess also from BioFit and ETIP Bioenergy websites. And as a consequence of not requiring prior registration, we don't have a list of participants. I think I spoke long enough. I ask Thies to give Rune presentation rights, and Rune, the floor will be yours.
Yes, perfect. So we can see the screen now of Mr. Lødeng. Just need to unmute you.
So, you see the full screen?
Yes, it works.
Yeah, that's good.
Please go ahead.
First, thanks to the organizers and for the introduction. It is a pleasure for me to give this presentation. The title is Bio-oil upgrading by co-HDO and co-HT. It is to some degree a technical presentation from work performed in the 4 refinery project, which is still ongoing. You see the list of people involved. And this project is coordinated by SINTEF and Duncan Aporiai. First, a brief outline of the content, some background information, the value chains and project objectives, then the scope of the study, technical challenges, and then some experimental aspects, including results and conclusions. This slide shows the value chains in for refinery. Target is production of renewable fuels from lignocellulose by integration in conventional refineries. Two primary biomass conversion technologies to bio-oils are targeted: hydrothermal liquefaction and pyrolysis. Refinery co-processing technologies addressed is including co-FCC, that is fluidized catalytic cracking, and co-hydro processing. And this presentation is focusing on the co-HDO and co-HT. Briefly on partners, it is SINTEF from Norway, CNRS from France, BTG from Netherlands, VTT from Finland, Repsol from Spain, Aalborg University from Denmark, E4 Tech from UK, and the oil company MOL from Hungary. This is the superior project objectives, and target is biofuels, understanding the value chains, and at the bottom line to define scenarios for the best possible implementation in existing refineries.
Rune, I'm sorry to interrupt you. Could you please turn on the presentation mode, which has been asked by your participants? Yeah, great, thanks.
The scope of VP3 is upgrading. It's about different aspects of process optimization, fractions of pyrolysis oil, and pyrolysis oil quality. It's about operating parameters, and it's about selecting the best catalyst. In co-HDO, we study mixtures of renewable oils only, 5 and 10% stabilized and deoxygenated pyrolysis oil, and 2.5% stabilized pyrolysis oil in rapeseed oil. The stabilized and deoxygenated oil is high quality oil, while the stabilized only is lower quality with higher oxygen content. In co-HT, we combine pyrolysis oil with fossil oils at the 5 and 10% levels of STPO. Some major technical challenges. First, it's about optimization of processing parameters. Learn about temperature, pressure, contact time to go in an optimal direction. For the catalyst, the lifetime is critical, especially because of the oxygen environment. The quality of the pyrolysis oil is important for lifetime, and quality determines the fraction that can be processed. And this quality is depending upon remaining oxygen levels, the reactive components level, and of potential contaminants that can cause deposits and accumulation. The upgrading is studied in a semi-pilot fixed bed reactor. We have used full pellet catalysts in all tests. It is a 1-inch internal diameter reactor. It's 1 meter long. The catalyst bed is typically 20 centimeter long, and the catalyst is diluted with silicium carbide to handle the heat release better. We have prepared and studied 2 different types of catalysts, the COMO on alumina and the NEMO on alumina. That is conventional materials. I will show results obtained under the NEMO sulfide catalyst, since this had a better time stability than the COMO. These catalysts are pretreated with dimethyl disulfide to activate them to the sulfide state. And this sulfur component is also added to the feed during the test to maintain the activity of the catalyst. Briefly on the analytical, We follow the gas composition by online gas chromatography. We calculate the hydrogen consumption. For the liquid products, we measure density, elements composition. We do a boiling point distribution, SIMDIST, and we also do chemical detailing by two-dimensional GCMS. And in addition, we follow the temperature, the catalyst bed behavior. The goal is production of middle distillates. Boiling points typically located between 150 and 360 degrees C. These graphs show the SIMDIST fingerprint of the feed oils. To the left, you see the fossil oils. They are largely inside the middle distillate range. The renewable oils in the right figure have a small fraction below 150 degrees C and 20% fraction above 360 degrees C. And you also see from the right figure that the SPO is more heavy than the more treated SDPO. A challenge for processing is the highly exothermal reaction. These profiles illustrate the difference of ordinary HDS that is not so highly exothermal compared to hydrodeoxygenation of rapeseed oil. Rapeseed oil is containing 11 weight % oxygen, so it's a rather high heat release. The HDO reaction is fast, and when performed at high conversion, much heat is released. And as a consequence, it is more difficult to control the reactor temperature in case of this high oxygen feedstock. Then some results. I'm not going into detail in this table, but each line in the table refers to 1 day on stream. So you see it's 16 days on stream approximately. We start the test with a fossil oil period, LGO, as a reference to see that things work nicely. Then this is followed by multiple rapeseed oil periods with variations in temperature, pressure, and so on. Then we switch to the co-feed in that you see in line 13 and 14. And then thereafter back again to LGO and rapeseed oil. The table shows via the density of the products obtained and via the remaining oxygen that the conditions give near complete HDO conversion between 99 and 100%. We also see via the HDS and HDN removal in these reference oil periods, that is the numbers in the red circles. You see that there is a slight activity decay over time, and that is one major challenge. The catalyst is not performing at the conventional level regarding lifetime stability. It's a slight decay to be observed over 16 days. Then light gases are formed. These are dominated when you look at the red boxes. It's propane and CO2 and carbon monoxide, but also other hydrocarbons. CO2 in this context is a loss. Carbon monoxide as well, but it is in addition a potential catalyst poison. C3 is value, and propane and the other hydrocarbons could be converted to, for example, hydrogen needed for the processing. The product liquid composition from rapeseed oil over time is shown here. This is dominated by linear C17 and C18 hydrocarbons. These two constitute above 80% of the liquid. In addition, there is some C15 and also some C19 and higher. So the total carbon yield in this system is above 90%. So this fingerprint shows the sim dist of the liquid product from RSO, and you see that the C19 plus fraction inside the red circle is that is a heavy fraction that is outside the middle distillate temperature interval. So this needs a solution to be used, for example, cracking or for hydrogen or something else that is useful. Then test 3, that's rapeseed oil with co-feeding of 10% SDPO and also 1.5% stabilized pyrolysis oil. It's approximately 12-day long test, and we see again from the density and also oxygen measurements that near complete conversion is reached. So the technical feasibility of doing this co-processing is demonstrated. Technically, there were no special issues for the 10% SDPO and the 2.5% SPO, but when we increased the SPO level to 5%, we started experiencing some pump instability issues. That was at the 5% level. Then to co-hydrotreating. This is this boiling point distribution of the co-feed mixture compared with the straight run gas oil. Straight run gas oil in red, mixture in blue. The SDPO fraction causes shifting of the boiling point a little in both ends, a little higher light fraction and a little more heavy fraction that is outside the middle distillate boiling window. It's a question about a few percent in total only. Another way of addressing time changes is via gravimetric density. So this shows the density of the liquid along the timeline of the test. So we see when we feed straight run gas oil only, it's a tendency to density increase, but when you step to the co-feed, including 10% SDPO, it might be that the tendency to increase is a little higher. It's not easy to evaluate, but it's an increase going on. Then we come to the nitrogen removal efficiency. I don't have the sulfur analysis ready yet, but the trend for this should be expected to be similar. We observe, as can be seen from the low part of the table, that the N removal efficiency is declining faster in presence of the co-feed. You see the weight percent ppm of nitrogen is increasing rather significantly. At this stage of the test, we also see some trace amount of oxygen. So this is additional evidence that some slow deactivation is proceeding. Then some hydrogen consumption estimates. Rapeseed oil as a reference, it has very high level of oxygen, 11 weight percent, and the hydrogen consumption is in the range of 200 to 250 normal liter per liter oil. When we add the 10% STPO, we are not able to measure any difference actually, because this STPO, it is also containing about 2% oxygen. This is removed, and in addition some hydrogen is used for saturation of other components. So all in all, it's not a big change. The fossil oil only, straight run gas oil, then the hydrogen consumption is in the range of 30 to 40 normal liter per liter oil, and that is 8 times lower. And for the straight run gas oil with STPO, we are not able to measure the difference. It is in the same range. Then I will conclude. The technical feasibility of co-HDO and co-HD has been demonstrated in semi-pilot scale with full pellet catalysts. We obtain a high yield of linear C17 and C18 from rapeseed oil. The major chemistry from the co-HDO is that the oxygen is deeply removed. The aromatics of the pyrolysis oil is converted to cyclic saturates. We have seen that the NEMO is more promising than the COMO, and we believe that is due to a better carbon monoxide tolerance. But as I have shown, we see a slow activity decay over 18 days. It's not clear if this is stabilizing or progressing further. And then regarding processing conditions, we think that higher pressure than 44 bars will be a benefit to lower olefins and likely also CO2, which is a loss. Regarding the levels, the fractions, STPO at 10% level is promising. It works well, and robustness to even higher fractions is likely. It is oil quality dependent though. A small fraction of 2.5% of the SPO is okay. When we increase this fraction, we enter some pump instability situation that we believe are caused by some particles. So it is possible that this must be fed separately, for example, not pre-mixed. The miscibility of 5 and 10% STPO with rapeseed oil is no issue. It mixes well. So then finally, thank you for your attention.
Thank you, Rune, for your contribution. This is very interesting and really hot off the press is my impression, the results you're presenting, and work is still ongoing in the fall refinery project. We have the possibility of asking questions through the chat box, but so far there have not been any. What we can also do, and let's try that for at least a few minutes, if you have a question, you can make yourself known, and then Thies as moderator can open your microphone, and so you can ask your question that way. And thirdly, there's the option that we take some questions really at the very end of the webinar. So let's see how it goes for the next 2-3 minutes, and I'll be back after that.
Okay, thank you very much, Rune. So we've got one question from Sylvain Verdier. So I would like to unmute you. If you could just ask a question to Rune, please.
Yes, can you hear me?
Yes, it works.
Yes, good. Very good presentation. I'm just curious to know how you check the miscibility of the pyrolysis oil with the rapeseed oil. Which technique you use exactly?
We use just do it in glass beakers beforehand to see that it mixes well. So we see visually that these are mixing well actually, and
Okay,
it's
so by visible inspection, visual inspection.
By inspection, and when you use, for example, stabilized pyrolysis oil, then you will see that you will form some solid materials when you come over a certain level. So but we have used pre-mixed feed, so I think the flexibility of feeding here will increase if you do separate feeding of the different oils. It's also some risk that if these oils are standing as a premix for a long time, you can have some precipitate. So yes, I think.
Good, perfect.
Yeah.
Thank you.
You're welcome.
So we've got another question from Ali Reza Yousefi. Please ask a question.
Okay, thanks. Thanks for the presentation. So I saw you mentioned the HTL oil is also being considered for this co-hydrotreating, co-hydrodeoxygenation or hydrocracker. I would like to know if you could just share some overview and insight in terms of comparing these two oils, which one works better with this co-processing work. Thanks.
Our experience with the HTL oil is that we haven't tested this in the co-hydrotreating mode. We have addressed miscibility of it in fossil oils and in rapeseed oils and so on. And I think this HTL oil, it's much more heavy than the pyrolysis oil. Maybe half the oil is above the middle distillate range. So as part of the project, it has been separated into fractions, for example, and tested. So I think it depends. You need a solution for the heavy fraction somewhere in the process.
Okay, thank you.
Yeah, thank you, Ali Reza. So for the moment, I don't see any further questions to Rune. If something should come up to your mind, of course, you can also ask in further course. So then I would like to give the word back to John.
Okay, perfect, Thies. And thanks, Rune, for your presentation and also for answering the questions that were raised. I will now hand on to the second speaker, which is Dr. Thijs Lammens. He's a senior process engineer at BIOFIT Bioliquids, and he will talk about methodologies for biogenic carbon determination when co-processing fast pyrolysis bio-oil. Thijs, the floor is yours.
You are still muted for the moment.
Thijs, we cannot hear you yet.
Yes, can you hear me now?
Now it's
Yes, it
fine.
works.
I'll mute myself.
Okay, great, thank you. So let me start again. Methodologies for biocarbon determination when co-processing fast pyrolysis bio-oil. It's a mouthful, and it's a bit less fancy research than what was just proposed, was just shown by Rune. But I do believe it's a very important topic to discuss when it comes to co-processing pyrolysis oil, for example, or other bio-oils when you make biofuels. Because in the end, it determines how much biofuel you produce, so how sustainable your product is in the end, and also whether you can comply with legislation, etc., etc. In this presentation, I want to cover a couple of topics. First, a short introduction about BTG Bioliquids and about pyrolysis oil co-processing. Then the two main topics of this presentation are radiocarbon analysis when you co-process pyrolysis oil in a FCC, a fluidized catalytic cracker, results of an experimental program we did. And then the second is the bookkeeping methodology, so other ways in which you can determine the bio-based content of the products from co-processing pyrolysis oil in an FCC unit. A case study based on literature data we did, and finally some conclusions and Q&A. About BTG and BTG bioliquids, just very short, because there's always a lot of confusion between the two. BTG bioliquids, where I work for, is a different company than BTG Biomass Technology Group, for which John works. We are in essence a spin-off of BTG about 10 years ago in order to commercialize the fast pyrolysis technology that was developed by BTG. We currently have 10 employees. We built the fast pyrolysis plant and Pyro in Hengelo, and we are currently constructing 2 more pyrolysis plants, one for Sweden and one for Finland. Then about fast pyrolysis, I think I'll just go through this one very, very quickly, because I assume most of the audience knows this, but it's the thermal cracking of organic material in the absence of oxygen. So what's most important, I think, when you talk about advanced biofuels, is that the typical feedstocks we use for fast pyrolysis are lignocellulosic feedstocks like sawdust, etc. So they are all the feedstocks, for example, in the Renewable Energy Directive, the famous Annex 9A feedstocks. Then about the pathways from fast pyrolysis oil to advanced biofuels. I have 3 different pathways here, which in essence cover the 3 presentations that we have today. So I think this works quite well. On the top you see a typical value chain or supply chain from crude oil to fuels through an oil refinery. And then based on what you do with the pyrolysis oil, you can either use the crude pyrolysis oil produced from biomass and then feed it directly into your oil refinery, or you can first hydrotreat it to make stabilized pyrolysis oil, and then you can co-feed it into a refinery. That's in essence what Rune just presented. What you can also do is that you completely hydrodeoxygenate your pyrolysis oil to what we call mixed transportation fuels. For example, a marine diesel could be part of this, and that's what the next presentation will be about. So I will focus on the first part, and that is co-processing crude fast pyrolysis bio-oil in an FCC unit in an oil refinery. In essence, what you do then is you use existing infrastructure, and that means that you have relatively low capex and production costs, a short time to market. You can quickly implement this route, and you can achieve a greenhouse gas reduction in fuels in the short term because of that. Here you see an overview of a typical complex refinery. I don't want to go into too much details, but what I want to show here is the catalytic cracking unit, the FCC, is typically the heart of a refinery. It takes on or can take on a lot of different feedstocks from different units, from different quality, etc. And it produces a whole range of different products. And because it can take so much different feedstocks, it's also the ideal unit to introduce pyrolysis oil, which is a very oxygen-rich feedstock, into a refinery, because it is actually able to handle it. The fact that you do produce a lot of different products, and that they may end up in a lot of different fuels and other products of a refinery is a bit of a problem when it comes to tracing the biocarbon, but I'll get back to that shortly. Before that, I want to say a little bit about scale, about the pyrolysis oil supply chain, and a comparison of scale between pyrolysis oil production and typical refineries. Here you see what we envisage for the supply chain for pyrolysis oil. So the idea is to locally convert the biomass where it is, close to the fields or close to the forest, or where the residue is released. This brings the added benefit that you can return the minerals back to the field, for example, so you don't transport a lot of minerals across the ocean, for example, if you would transport the biomass with it. If you liquefy biomass by doing pyrolysis, the density increases greatly, so it gives you a lot better, more efficient logistics. And then you can do a centralized further processing and distribution in existing infrastructure. When you talk about a refinery co-processing of pyrolysis oil, here I add some numbers. If you have a typical FCC unit of a European refinery, it's about 40 to 50,000 barrels per day. FCC unit, if you then co-process 5 weight percent pyrolysis oil, you end up with roughly 2 weight percent advanced biofuels. In order to do that, you need about 460 tons per day of pyrolysis oil, which translates back to 6 decentral fast pyrolysis plants of the size of Empyro or the 2 plants that we are currently building in Scandinavia. So that gives a bit of an idea of scale. So roughly for every weight percent that you want to co-process in an FCC unit, you need 1 pyrolysis plant. So there is quite a significant scale difference there. Then how does it work? What you see here is a scheme of a typical FCC unit. I don't want to go into all the technical details here at that point. In black, it's sort of the traditional unit. You have a VGO, a petroleum feed that goes into your unit. It's cracked with a catalyst, and in the end, you make a range of products. What you do when you co-process pyrolysis oil is you just add the pyrolysis oil as a separate feed into the unit, and it's cracked together with your regular petroleum feed to produce these same products. This means that the green carbon that you introduce, it is distributed across all the different products that you produce. And that brings me to the main question for my presentation here today, which is how to trace the biogenic carbon. So currently, if you look at supply chains and tracing biogenic carbon through supply chains for biochemicals, biofuels, it's fairly easy and well established. When you talk about products with a high percentage of biogenic carbon, also when you talk about co-processing vegetable oils in hydrotreaters to produce HVO, it's also well established how to trace the biogenic carbon then. And there is a whole certification system for such pathways, for example, by the ISCC, which rely on either radiocarbon, so C14 determination, or bookkeeping methods like mass or energy balances. However, when you talk about pyrolysis oil, I believe that the combination of challenges is relatively unique compared to the other scenarios. The scale difference I mentioned, there's a scale difference of about 1 to 100 between a pyrolysis plant and an FCC unit. When you co-process pyrolysis oil, crude pyrolysis oil, you are limited to in the order of 5 weight percent of pyrolysis oil that you can feed without introducing major technical changes to your FCC unit. And the green carbon is distributed across many refinery products. So on the one hand, you have sort of a dilution of your biogenic carbon by scale. And on the other hand, you have a dilution because it's distributed amongst many different products. And a bit of a spoiler alert, but this makes radiocarbon analysis an unfeasible method to my view, and I will show that in the next part of the presentation. So about radiocarbon analysis for co-processing pyrolysis oil. First of all, what's known already? In 2017, Petrobras published some data. They did large-scale pilot plant trials of pyrolysis oil co-processing in their FCC unit, and they also did radiocarbon analysis of the products. And what they showed is that if you use 5% bio-oil in the feed, you have about 1 weight percent of biogenic carbon in your liquid product. and then it sort of linearly increases with 10 and 2 and 20 and 5%. However, as I said, because of this scale difference, refiners will start with about 1 weight percent co-processing and then build up until 5 weight percent. For example, the plant that we are currently building in Sweden, the pyrolysis oil that is going to be produced there will be used for co-processing in a refinery. And then also you talk about in terms of volume, about 1 weight percent. So that means that you are really in this red boxed area when it comes to the percentage of bio oil that you're feeding into your unit. If you would linearly interpolate this graph, that means that the biocarbon percentage would be between sort of 0.2 and 1 weight percent, which is very, very low to be able to determine it. Different stakeholders claim that you can actually determine these numbers reliably, but I have some doubts, and that's why we did a test campaign with the question is, can we really reliably determine a radiocarbon in this marked range? And I'll skip, in view of time, I'll skip immediately to the results. I'll show later, we published a paper on it recently. I'll send a link that you can find out all the details, etc. In essence, what we did here is we used samples from Petrobras trials in the same pilot plant. We diluted them to known concentrations and then submitted them for analysis by C14 by the method of AMS, so the accelerated mass spectroscopy, which is the most accurate and most precise method that exists for doing radiocarbon analysis, and the most expensive, by the way. And what you see here is you see a graph with a lot of points, blue points and orange points, which are the samples, and they have error bars, which are the error margins that were indicated by the lab. And that should show that the error margin is actually fairly small and the results are reliable. But as you can see, if you draw a line through them, it should be linear, but there's really a lot of data scatter. And I think you can conclude from this that in this marked range in here, there's really a lot of uncertainty in this method. If you translate this radiocarbon analysis into a biogenic carbon analysis, is what you see on the graph on the right. The ASTM standard that exists for doing this analysis, it prescribes that you need to take an error margin of 3% biocarbon in absolute values into account because of the uncertainties that I've just shown. So that means that you're talking from 0 to 2 weight percent plus or minus 3 weight percent. So these are sort of the actual error margins if you take the current ASTM norm into account. And that just summarizes this, that there is a lot of uncertainty in this method. One of the reasons, and now I'm going into a bit more detail, but one of the reasons for the ASTM to introduce such high error margins is what they call the atmospheric adjustment factor. C14 is created by radioactive radiation in the atmosphere, coming from the sun, but also coming from, for example, atom bomb testing in the past century, and it's that those things really influence the amount of radiocarbon that's in the atmosphere, and thus the amount of radiocarbon that's in your trees, for example, if you make your pyrolysis oil from sawdust, as in our case. And that really influences the amount of biocarbon that in the end you determine. And this graph shows that for all our samples, we were 15% too high in actual biocarbon, or in measured biocarbon content compared to the actual data. So this really shows that there's a sort of a structural difference that depends on your feedstock that you use for producing pyrolysis oil. So if you use an agricultural residue like straw, you will get different numbers than when you use sawdust from trees from Scandinavia, which will give different results than when you would use sawdust from trees from the United States, for example. So there's really an error margin that is introduced in this way as well. This brings me to my conclusions on radiocarbon analysis for this presentation, which is we started with gasoline, LCO or FCC diesel, and total liquid product samples. I showed only the results from the LCO. You can see the other results also in our paper. And we analyzed them for biogenic content. Knowing that ASTM prescribes an absolute error margin of 3 weight % biogenic carbon, and that the statistical limit of detection of this is 0.4% of C14. The goal was to assess the suitability of this analysis for determining the biogenic content when you co-process small amounts of pyrolysis oil. What we observed was that there's really significant deviations and a large data scatter. Also that the atmospheric adjustment factor as prescribed by ASTM, in this case 1.0, doesn't match the actual C14 that was in the products, probably because of this atom bomb effect that I was referring to. So we believe that when you co-process such small amounts of pyrolysis oil in a commercial situation, you really cannot rely on C14 analysis to do these kind of biogenic carbon determination. And that means that you need to do something else, which brings me to the next part of this presentation, the bookkeeping methods that you can use to do this. What we did is a case study based on, for transparency sake, we used published data in literature by Petrobras, again, by their unit. The yields that I used are, you see here in this graph, so different products that are made from if you co-process 100% VGO or if you would co-process 5% pyrolysis oil with it. And the goal was to evaluate and compare the different methods that exist for pyrolysis oil co-processing. We evaluated 5 different methods, one based on observed yields, a carbon mass balance, a total mass balance method, energy balance method, and a free attribution method. The first one, the observed yields, really looks at what happens. So you have a baseline with only your VGO, and you look at, okay, how do the yields change? And we attribute these changes to biofuel production, so to the co-processing. And then there's the carbon and the total mass balances, which really calculate the yields based on the input. In the case of the carbon mass balance on the biocarbon input, in case of the total mass balance on the total biomass input. And then these methods say, okay, when you do biomass co-processing, you introduce oxygen, so that will be released partly in CO, CO2, and water. So these products we subtract from the amount of biomass that you actually put in. So that's sort of a way to compensate for the oxygen that you put in, which will lead to less biofuel production than the actual mass that you are putting in. Then there's an energy balance method, which is a bit similar, but then it's calculated on the basis of energy content of the biomass or the pyrolysis oil input and all the products that go out. And there's a free attribution method, which is common for the chemical industry, but not so much for biofuels production, where you just freely attribute as an economic operator, you attribute the biomass that you put into your system to a certain product or multiple products that you want to get credits from, for example. In view of time, I won't go into the results of all these methods, but I want to show them for 2, namely the observed yields and the energy balance method. If you use the observed yields method based on the data that from Petrobras that I showed, you start with the baseline scenario without any renewable feedstock, and then you add your pyrolysis oil. Then actually this graph is what you see. So from the products, you see an increase of LPG, gasoline, and LCO. but you see a relative decrease of dry gas, fuel oil, and coke. And then, of course, you see the CO, the CO2, and the water I was referring to earlier. So what you actually see is relatively you produce more gasoline, LPG, and LCO, and you decrease these products when you add pyrolysis oil. If you then calculate the total biofuels yield, in this case LPG, gasoline, LCO, and the fuel oil, if you add it together, then you have a yield of about 56% of biofuels from your pyrolysis oil. This is a bit an overestimation, I believe, personally, because of these negative yields. It would be fairer to subtract them from the positive yields, because you cannot produce negative yields from a certain product. So when you really talk about biogenic carbon determination and where the biocarbon is actually going, then you need to adapt your method for this effect. Which you can do by subtracting these negative yields of dry gas, fuel oil, and coke that I just showed, and you subtract them from the positive yields, and then you get sort of more reliable yields of the LPG, gasoline, and LCO. And then you talk about a total biofuels yield of about 44%. Again, of course, the CO, the CO2, and the water, they don't change in this. Another way you could do is an energy balance method, where you distribute the renewable input across all the products based on the energy content of the feedstocks and the products. And the losses to CO, CO2, and water are automatically incorporated here, because they don't have an energy content, so they don't give you anything. If you do this calculation, you look again at the LPG, gasoline, LCO, and fuel oil that are produced, the total yield is 36. The only difference with the previous method is, of course, that you now produce more a positive amount of fuel oil and coke and dry gas, which goes at the expense of the LPG, gasoline, and LCO production. Then this is an overview of all the methods that we analyzed. And it shows that if you look at the total yields, it's all between the 400 and 500 kilogram of biofuel of total products from 1 ton of pyrolysis oil. So it's in the same range, but you see, of course, some differences. What I showed, if you use the observed yield methods, there's no dry gas and no fuel oil and no coke, so you have more LPG, gasoline, and LCO, that's the blue bars, compared to energy and mass balance methods, the orange and the green ones. And if you do a free attribution, you can of course choose where this gray bar is. So for the sake of an example here, I picked between gasoline and diesel as 50-50. Which brings me to the conclusions of this part, and that is that if you use an observed yields method, it gives you both positive and negative yields. So the current method as it exists, it doesn't really account for this. So therefore, we adapted it in order to avoid an overestimation of biofuel yields. And then you have the carbon mass, total mass, and energy balance methods. They showed slightly different results. I haven't shown that in this presentation. You can read that back in the paper. This is probably due to some inaccuracies in the oxygen balance of the experiments in the paper we based this on, and also because we had to estimate the energy content of all the different products. They weren't published with the products in this paper, so there may be some inaccuracies there as well. From these three, the energy balance method gave the lowest yields, but it's sort of in the same range. And we believe that an energy balance method is going to be the easiest for refiners probably to implement, and with that also the most reliable. Free attribution is of course a very straightforward and easy to implement method. However, it's prone to strong criticism by stakeholders. So it's the question if it would be a feasible method to use for biofuels. my conclusions for this, based on what I've shown, is that the observed yields in the adapted form that are presented and the energy balance methods are really the most suitable bookkeeping methods when you talk about FCC co-processing of pyrolysis oil at small percentages, so below 5 or 8%. And then, of course, when you trace your biocarbon through the entire supply chain, you can verify the renewable input that goes into your refinery. You can do that with radiocarbon analysis, because if you have 100% pyrolysis oil, these inaccuracies, they are only minimal compared to when you use only 1 or 2 weight percent. So the pyrolysis oil, before you feed it into the refinery, of course, you can verify that being biogenic with radiocarbon analysis. Then the overall conclusions in Q&A. In conclusion, co-processing pyrolysis oil in FCC units uses existing infrastructure. It has a lot of potential as a pathway to advanced biofuels because of the low capex and production costs and the short time to market. And that also means that you can achieve significant greenhouse gas emission reductions really on the short term, which is needed for the European climate goals. Biogenic carbon tracing, however, is particularly challenging if you use this pathway, because of the scale difference and the co-processing percentages, and because the green carbon is distributed across many different products. So radiocarbon analysis is really unfeasible for commercial purposes. We show that with experimental data that I showed. And bookkeeping methods, they are appropriate for this pathway. And then especially we believe the observed yields method in its modified form and the energy balance method are the most suitable methods. And then in order to verify the biocarbon content throughout the entire supply chain, you can still verify the renewable input that you put into your refinery with radiocarbon analysis. That was it for my presentation today. I believe these slides will probably be shared or will maybe be shared, but in any case, if you want to read more, we published a paper on white paper on FCC co-processing in general, which you can find on our website www.btgbtl.com. And also specifically relevant for this presentation, a white paper on pyrolysis oil biocarbon tracing, which you can find on our website as well. Also, feel free to send any additional questions directly to my email address, which you see in this slide as well. That was it. Thank you very much for your attention. And if there's any questions, I'm happy to answer some if there's still enough time.
Yeah, thank you very much, Thijs. So for the moment, I did not receive any questions in the chat box. So if you have anything you would like to know from Thijs Lammens, please forward your questions in the notebook and the chat box, and then I can unmute you so that you can ask the questions directly to him. But since we have no questions for the moment, yeah, I think John, please go ahead.
Okay, thanks Thijs and Thies. Almost the same name, just a different language. Very interesting overview. Thijs, you did use up all your time, I have to admit. So if there are any questions, we can do them after the last presentation. So I'd like to introduce our last speaker, which is Bert van der Belt. He's the technology director at the mother company, so to say, at BTG Biomass Technology Group. He will talk, like the other speakers, about really the latest developments in the field of pyrolysis oil, and in this case, on the production of advanced transport fuels. Bert, the floor is yours.
Thank you, John, for this introduction, and thanks for giving me the opportunity to present today. Of course, also the subject of my presentation is advanced biofuels from pyrolysis oil, and a lot has already been sent in the previous presentation, so my presentation will be a little bit shorter than the previous one. You have seen this picture before, and it's the it's an overview of the refinery and the different options which are there for producing transportation fuels from pyrolysis oil. As mentioned, the green line was presented by Thijs and the blue line by Rune. I will focus on the yellow line, and that means standalone production of advanced biofuels directly from pyrolysis oil. And in this case, I will focus more on the production of marine biofuels from pyrolysis oil. Well, if you look at pyrolysis oil and the composition, you see a typical composition of fast pyrolysis oil on the left side, and on the right-hand side, a marine distillate fuel. We're looking mainly at the distillate fuels. And if you look at a few parameters like water content, in pyrolysis oil we have about 25% and a marine fuel is virtually free of any water. The density of pyrolysis oil is close to 1200, and we have to reduce to below 900. The heating value is only 16, and we have to increase to 42. The acid number is also an important one. Pyrolysis oil is acidic, and we have to reduce the acid number by more than a factor of 100. Sulfur is not really a problem. It's quite low, and it complies with current specifications. Flash point of pyrolysis oil is a little bit unclear and difficult to measure. It's unreliable and with a large scatter, and normally the value doesn't say that much, so it's a little bit of a question mark. Well, the flash point for marine fuel should be above 55 or 60. One other thing, if we want to use it in an engine or in a ship engine, a cetane number might be of relevance. For pyrolysis oil, it's below 20, and some people even say it's below 0, so it's difficult to ignite in an engine, whereas the cetane number for a marine fuel should be above 40. And so pyrolysis oil, it is a fuel. It's really a fuel. It's used as a fuel, but pyrolysis oil is certainly not an oil. And the question is, of course, how to come from pyrolysis oil, what to do or to upgrade and to make a marine fuel. Before going to the process, it's not only the properties, we should also know something about the composition. And going a little bit back, if you look at fast pyrolysis of lignocellulosic biomass, it typically consists of hemicellulose, cellulose, lignin, and extractors. And if you do the fast pyrolysis process, the hemicellulose typically leads to the acids, the ketones, aldehydes. Cellulose is depolymerized to carbohydrates, sugars or sugar fragments. Lignin, we get what we call pyrolytic lignin, but it's mainly the phenolic and aromatic structures which are in the original lignin, and it is kind of depolymerization. Then we have the extractives and the rosins, the fatty acids. They are also present in the pyrolysis liquid, and we have water. And in fact, we need a process to convert this kind of components into the marine fuel. So if you go to the process, it was already presented in the previous presentations. You can do a hydro treatment of pyrolysis oil, but you cannot simply replace the feedstock of a conventional hydrotreater by pyrolysis oil. It will not work. And what we actually need is a two-step upgrading process, at least 2 steps. And the first step is what we call a stabilization, and the stabilization mainly converts the sugars to something which can be used in standard processing. What we do in this first step, it's more sugar chemistry. We need a dedicated catalyst, and the catalyst, we have our own proprietary catalyst. We call it Picola. We need a pressure, or we normally operate at a pressure of 200 bar, is quite high. We need a temperature ramping, so we have different temperature ranges within the reactor, starting somewhere around 100 degrees, and we can go up to maybe 300 degrees C. The space velocity somewhere in range 0.2 to 0.5, and the product from this first step, that's what we call this SPO. This SPO is sent to the second step, and the second step is more conventional hydrotreatment. We use a standard catalyst, a sulfided NEMO or COMO, and normally, most often, it's a sulfided NEMO. The pressure can be a little bit lower, and we still operate around 100 to 140 bar. Also in this case, we have a temperature ramping starting around 250, and we can go up to 450. It's not always necessary, but that's our maximum. And the space velocity is also a little bit higher than for the first step. If you combine both steps, then you end up with a kind of a standalone upgrading to a transportation fuel. The overall hydrogen consumption is around 5% based on the incoming pyrolysis oil. And the product from the second step of after the complete treatment, it's a distillable, it's a mixed transportation fuel, what we call this MTF. We can further illustrate this process in these two graphs. What you see on the left-hand side is the deoxygenation degree, the amount of oxygen removed from the pyrolysis oil as a function of the hydrogen consumption. And this relation, it's not a linear relation. For instance, initially you start with consuming hydrogen, but you don't see any change in oxygen content. And the explanation is you start with the effect with carbohydrates hydrogenation. It means it's taking up hydrogen, but it does not remove any oxygen. And so you can find different reactions, different ongoing reactions as a function of time and temperature and so on. This first part, the green area, it's more where we use this picolar catalyst, and after that we switch to a sulfided Nemo-Como. And so we have a carbohydrate hydrogenation, carbohydrate deoxygenation, and then we also have this dehydration, removing water from the system. You get some olefins and aldehyde hydrogenation, and the final step is in fact this lignin hydrocracking. And after these steps, we are close to this 5-8%, a little bit below 5-8% of hydrogen consumption, and then it's more or less oxygen free or very low in oxygen, let's say at least below 1%. The same is also illustrated in the figure on the right-hand side. It's a so-called Van Krevelen plot. And also the marks you see in both graphs, it's based on experimental work. At the top, you see this FPBO, the pyrolysis oil. You have some hydrogenation, also of the sugars, you have dehydration, and then deoxygenation cracking. And finally, you end up with a mixed transportation fuel. What you also see is the initial start is a sugar chemistry, then you have dehydration, and at the end is the lignin chemistry. And it's really two different areas, the sugar chemistry and lignin chemistry. It's also different conditions, different catalysts. And you can simply not do it in one step by one temperature, one pressure, one catalyst. It does not work. At least that's our experience over the last, let's say, 10, 15 years. So what next? Then you have to make a process. Well, this is what you would expect then. You start with fast pyrolysis oil, you feed it to a first reactor filled with the picolar catalyst operating at 200 bar. You add this hydrogen. Hydrogen, of course, is required. Preferably, the hydrogen is from a renewable source and is needed in both steps. So the output of the first reactor is the SPO sent to the second reactor where we have this standard hydrotreating catalyst. And then you get this MTF, what we call the drop-in biofuel. What is this drop-in biofuel? It's illustrated on this graph. The left and the right-hand side you have seen before. In the middle now, I added the results from our own experimental work. And that's what we call the biofuel, the MTF. If you look at the water content, at least it's quite low and it's below 0.1 weight%. Sometimes you can still find some water. The density is now at 870, so below the target. The heating value at least above 40, and normally we measure 42, 43, somewhere in that range. It means that's quite good. The S number has been reduced to below 0.15, and very often it's even much lower. And so acidity almost completely disappeared. Sulfur is not a problem because we also had limited sulfur in the feedstock. Of course, in the second step, we add some sulfur to sulfide the catalyst, but still in the product it's quite low. Flash point 25, that's an issue. I will come back to that. The cetane number we don't know yet. There is research ongoing with the University of Eindhoven and Good Fuels to determine the combustion properties. There will be some testing also in a small engine, but to get a better view on what are the exact combustion properties, because these should also be compatible with existing normal ship engines. As mentioned, this flash point of 25 degrees C, that is an issue, because it's a flash point is important for storage also on ships, logistics and so on. And so we have to do something on this about this flash point, or we are looking at what to do with this flash point. And well, that's illustrated here. We are mainly interested in to make blends with conventional shipping fuel. So we make a biofuel, mix it with for instance, this distillate marine fuels. And what we observed, it is fully miscible. So there's no phase separation, no deposits. It mixes very well. But the flash point of the MTF is what we normally see in the range of 10 to 30 degrees C, which is quite low. And if you add it to a standard fuel, you can only add a little bit, and then the flash point drops below the minimum, and that's not allowed. That's illustrated in the graph on the right-hand side, and that's we plotted the flash point as a function of the biofuel content, and the biofuel content means it's a blend of the biofuel, the MTF, and just standard diesel. So completely on the right-hand side is 100% biofuel. You see the green dots. This fuel had a flash point of 27, and if you mix it with diesel, it's going up. And let's say we assumed for a long time the minimum is 55 degrees C for flash point, and you can only add some 10% of the complete fuel, and then just reaching the boundary of flash point. To increase the flash point of the biofuel, of the low flash point of the biofuel is caused by some lights present in the biofuel. So what we try to do is just by simple flash or simple distillation, remove part of the lights from the fuel. And what you see, the blue dots, the blue line is for a biofuel. It's the 85% MTF residue. It means we removed 50% of light components from the pyrolysis oil. And it already increased the flash point to 52 in this case. And if you still assume the boundary of 55 degrees C, we can now add something like 75% of this biofuel. We can add it to a standard marine fuel and still complying with the flash point limit. The other thing what we do at the moment, and that's interesting for different reasons, and it's available nowadays, it's this hydrotreated vegetable oil. And the interesting thing is that the flash point of HVO is quite high, and what we measured is around 77. It gives some extra room for adding fuels with a lower flash point. So we mixed HVO also with this kind of things, and then for instance, the blue lines, the blue dots will also further go up, and we comply with it nearly over the whole range. So HVO it's an interesting mixing for us, and it's also renewable, so that makes it interesting. If you look at the lights, so this 15% which has been removed from the biofuel, there is some benzene, there's a little bit of octane, but the majority of these lights, it's cyclohexanes, and methyl, ethyl, and propyl cyclohexane, and the majority it's a little bit on propyl side. So that's the composition of the lights, but it also explains the low flash point. We try to measure it, but we can't go below 10, and the flash point of this lights is really below 10, and so it's a really light fuel. It's more like gasoline, and it burns quite easily. So this is about the properties. So where are we today, and what is our ambition? And that's a little bit shown on this slide. We aim for a demonstration plant in 2023. So in 3 years' time, we would like to have a demo plant up and running. And the demonstration plant should be a kind of a pre-commercial plant. Roughly, we are thinking about a capacity of 1,000 tons per year output. That's roughly 20 barrels per day. So It's still pre-commercial. It's not large enough for commercial operation, but still a significant plant. And that's where we want to go. If you look at the different elements of relevant for the realization of such demonstration plant, fast pyrolysis, as I already mentioned in the previous presentation, fast pyrolysis is commercial. You can buy it commercially. It is implemented nowadays. There are plants in the Netherlands, in Scandinavia. Pyrolysis oil is there. I also showed that we can make a drop-in biofuel from fast pyrolysis oil by at least by two-step hydrogenation process. We make something which is close already to the specification of a marine biofuel. We are still doing research. We have our own hydrotreated pilot plant at BTG. It has an input of about 50 kilograms per day, and it gives also the possibility to produce some larger quantities, to do some engine testing, and that's also something going up. And another important part is, of course, the picolar catalyst. We produce tens of kilograms, but if you go to a demonstration, also the catalyst needs scaling up, and that's also something we are working on. But it's all aiming at the realization of a demonstration plant in, let's say, a 3 years time frame. So that brings me to a summary. Or the major conclusions. We can upgrade fast pyrolysis oil to an advanced drop-in liquid biofuel. We need a two-step hydrotreating process, and the most critical part is the first step of the upgrading and the stabilization, and it needs a dedicated catalyst. Initially, we are targeting the shipping sector, and in particular blending this fuel with marine distillate fuels. That would be our approach. And finally, our ambition is to demonstrate this pyrolysis oil upgrading on a pre-commercial scale of let's say 1,000 tons per year, and that's an estimate, and in a 3 years time frame. And that brings me to the end of this presentation. Thank you for your attention.
Yeah, thank you very much, Bert. So we've got a question from Christoph Strasser. I will just unmute him. Christoph Strasser, please go ahead.
Hello, can you hear me?
Yes,
Yeah, I just wanted to ask you, what about the total production costs for this MTF in euro per megawatt hour? Have you already some calculations for that?
We do have calculations for a full-scale plant or commercial plant, and we did some initial calculations. And we think a minimum commercial size would be something like 10 tons an hour. It means that you have to go through something like 30,000 tons of product per year, and that's commercial. The demonstration plant is about a factor of 20 smaller. And if you calculate for a demonstration plant, the price will be extremely high.
Yeah, of course.
Did a calculation for the full-scale plant, and then you end up somewhere in this range of 900 to 1,300 euros per ton. But of course, there is also a strong influence of the, particularly of the feedstock and the pyrolysis oil and the hydrogen and the origin of the hydrogen. If you really have renewable hydrogen nowadays, it makes also this product quite expensive because renewable hydrogen is expensive. The same also a little bit for pyrolysis oil, depending on where you are. The two major cost factors is hydrogen and pyrolysis oil.
Yeah, okay. Thank you.
Okay, are there any other questions from the participants in the chat box? So far, we don't have any additional questions. So if you would like to ask something to Bert van der Belt or our two former speakers, please just send me a short note in the chat box. Okay, so for the moment we don't have any additional questions, John. So in case you would like to know anything and the follow-up of this webinar, you can of course also send us an email and we will forward it to the presenters, or as you have the email addresses on the screen. Of course, you can also contact the speakers directly.
Yeah, T, thank you for moderating the Q&A session, which was not too difficult today, but I think you approached it very nicely by opening the microphones of the people that asked questions. I'd like to say thank you for the speakers for their presentations. It was a nice overview of really state-of-the-art developments taking place at the moment in this interesting field of the upgrading of pyrolysis oil. Thanks to the audience for your participation and for your questions. We had about 70 people all the time. Some dropped in, some dropped out during the webinar, but still a considerable number considering we're discussing a highly specific technical issue. The webinar recordings will be placed online soon. We haven't collected your email contacts, so it's not possible for us to send you a personal message. But in case you want to receive a warning, please let one of the organizers know, or you can send an email to me or to Bert. My email address is vos@bggworld.com. Bert's address is here on the screen. You probably have 20 seconds to write it down by hand if needed. The organizing projects, this is Music, BioFit and ETIP Bioenergy. They plan to organize more webinars this year and next year. Plans for these are under development. Most likely the first topic to be addressed is going to be torrefaction of biomass. Keep an eye out on our websites and on our socials, or drop us a line if you're interested. Also on my end, thank you very much for your attention, and we hope to see you back sometime soon at one of our future events.